Let's define what a second-order differential equation is. First, a differential equation is an equation that relates an unknown function with one or more of its derivatives. A second-order differential equation is a differential equation where the highest derivative of the unknown function is the second derivative. In general, a second-order differential equation can be written in the form capital F of xy, y prime, and y double prime equals 0, where y is the unknown function of the independent variable x. Y represents the first derivative of y with respect to x. Y represents the second derivative of y with respect to x. And f is some function that relates x, y, and the first and second derivatives. Often, we can rearrange the equation to explicitly solve for the second derivative. Y double prime equals lowercase f of x, y, y underscore prime. A classic example of a second-order differential equation comes from physics, describing simple harmonic motion, like a mass oscillating on a spring, d squared y over dt squared, plus omega squared y equals 0. In this equation, the unknown function, y, is the displacement of the object at time t. D squared y over dt squared, or y double prime, is the second derivative of displacement with respect to time, which represents the acceleration of the spring. Omega squared is a constant where omega is the angular frequency of the oscillation. Since the highest derivative is the second derivative, this makes it a second-order differential equation. A possible solution to this equation is y of t equals capital A cosine omega t plus capital B sine omega t, where A and B are constants determined by initial conditions. And that is a wrap on second-order differential equations.